So welcome back, everyone. This is day 2 of the workshop. So today we're going to talk a little bit about some basic outputs and basic inputs that you connect to an Arduino, how would you set that up electronically, and then also how you would program in receiving that data and processing it. So we're just going to talk about one output today, but that's the LED, which we used before. LED stands for light emitting diode. So when you pass current through the diode, it lights up. It's pretty simple. It does have a polarity, which means one side has to be connected to positive and one side has to be connected to negative. The positive side is the anode, and that's the longer lead, and the cathode's the shorter lead. If you connect it in reverse, it won't damage the diode, but it will not light up. It just won't work. So the RGB LED is the advanced version. So it's basically 3 LEDs in one. So you got a red, green, and blue, and then it has a common ground, which is this longest pin. So because light is made up of red light, green light, blue light, if you vary these values, you can get basically any color that you want. If you have them all on really bright, it's white light. And if you vary them in different ways, it could be a whole spectrum of colors. And this is how we'll connect it up later today. So each of the channels will have its own digital input or digital output, and then we'll connect the center one to ground. So for inputs, very simple input, just like a button or a switch. When you press it, there's either normally open or normally closed. So a normally open would be when you press it, the contacts close and it allows current to flow. Normally closed would be that normally it allows current to flow, and when you press it, it opens up and no longer current can flow. Normally open push buttons are what we normally think of when a button, like when you press it, something happens. Sometimes normally closed push buttons are good as safeties. So when you press it, you remove electric power from the system, and that's a safer way to do it maybe. This is what they commonly look like in these small circuits, and it's important to note that these legs across from each other are connected together. So if you connect your pins directly like this, it won't work. It'll always be connected whether the button's pressed or not. So you want to make sure you connect it diagonally. Also, I don't know who here has taken digital 273, but I think most people know what an AND gate is and what an OR gate is. And you can simulate that with buttons. So if you put buttons in series, you have to press them both. You have to press the first one and the second one to light up the light bulb. If you put them in parallel, it's simulates OR logic. So that's probably more than we need to know about buttons. But a potentiometer is a variable resistor. So looks like this. It has this resistive material around the outside, and then this wiper that you can either spin or maybe with a screwdriver turn to a certain position. So as you move that wiper, the resistance, say you're turning it clockwise, the resistance between the center pin and the right pin is going to decrease because this wiper is going to move this way and there's going to be less resistive material. And at the same time, there's the resistance between the left pin and the center pin is going to increase because there's going to be more resistive material. So that's kind of what it looks like on the inside. This is typically how it's drawn in circuits, like in circuit diagrams. It's great for fine-tuning a circuit when you want an exact resistance, or when you want to be able to adjust the circuit on the fly, maybe adjusting the brightness of an LED. They can also act as a voltage divider by themselves, and we'll talk about what that means in a minute. Photoresistor is also a variable resistor, but it changes its resistance based on light. So the more light, or the resistance decreases as the light intensity increases. So it's just like this one, but instead of you're able to change the resistance, it does it based on how much light is present. And then obviously there's many more inputs or different inputs that we could connect to the Arduino. We have ultrasonic sensors that you've probably seen lying around our workspace, infrared sensors, force sensors, accelerometers, temperature sensors, many different sensors we can work with. And how we connect I think that's the next thing I talk about. When we connect sensors, there's typically 3 ways that we connect it. It can either be a digital input, so like a push button. If you remember from last time what digital and analog is, push button would be digital. It's either on or it's off. Something like a potentiometer or a photoresistor is analog. Its voltage or its value can change over a set range. So we can use analog inputs for these. And then the final one is slightly different, but for some of these that have a very precise value, like a temperature sensor, an accelerometer, and that value is going to change, we don't want to just use analog signals because those aren't the most precise. And normally that's fine. Like if you're dealing with how much light is present, it's okay if it's off by a little bit. But for certain sensors like temperature sensors, accelerometers, force sensors, we'll have to use some sort of communication protocol to pass a value back and forth. If the temperature is exactly 78.53 degrees, we want to pass that exact number. And we can do that with different communication protocols, which we'll talk about in a future lesson. Any questions so far? Relatively basic stuff so far. We want to talk about connecting sensors. So some of these sensors, they have a change in resistance based on the given, what did I say? The sensors change in resistance based on whatever value it's measuring. The Arduino, though, it doesn't measure a change in resistance or a change in current. It measures a change in voltage. So we have to figure out how we can connect sensors to the Arduino so we can measure that change in voltage. Before we do that, real quick, hopefully everyone remembers this. With resistors, the basic building block in a lot of circuits, if you put resistors in series, you just add the resistance together. If you put this resistors in parallel, there's a fancy formula, but it's easy to remember that if it's the same value, if R1 and R2 are the same value, the total resistance is cut in half. So if these are both 100 ohm resistors, in this instance, the total resistance would be 200. In this instance, the total resistance would be 50. Basic stuff. This is the voltage divider, which is very useful in circuits. So how it works is, say with the Arduino, we use 5 volts. But say we have something that we want to have operate at a different voltage, we could use a voltage divider to achieve this. So using this formula, we can adjust R1 and R2 to get the correct V out. And if we want to know a little bit more how this formula happens, if you look on the whiteboard, so this is the same circuit, voltage that's given, voltage out, which is what we desire. Because both of these resistors are in series and there's only one loop, there's one current in the circuit, and then these values can change and are different. So if we want to know what the current or what the voltage is here, just using Ohm's law, we've got V out equals I R2. Because remember, there's only one current, it's the same throughout the whole circuit. Then basic math, if we can put something on the numerator and in the denominator to cancel out. So we're just going to put voltage 1 here and here. Then we're going to expand voltage 1, because using Ohm's law, voltage 1 equals the current plus both of these resistors. So we got R1 plus R2. And then we can cancel out current, and so we have V out equals V1 R2 over R1 plus R2. So using this formula, we can decide if we want this to be a specific value and we have a set input voltage, we can change these resistors to get the value that we want. Another useful thing is if we have a set resistor and then a resistance that's changing, we can measure that change by measuring the voltage here. So using the Arduino that measures changes in voltage, we can notice a change in resistance. So what we're going to do later is we're going to connect the photoresistor, and it's going to be part of this circuit. It's going to be R1, and we can measure that change through the voltage that changes here. Any questions about that? That probably didn't come up too well on the sound, but hopefully I talked loud enough. So then also, as I mentioned before, a potentiometer can act as a voltage divider by itself because you basically have two resistors in one. You have this resistive material and this resistive material. So say we have 5 volts and it has to be dropped. All 5 volts has to be dropped between this pin and this pin. The voltage that's present on the middle pin will change depending on where the wiper is. If the wiper is all the way to the left, then there's going to be only a little bit of this resistive material, so it's going to be a small resistance, so it's going to drop a small voltage. So maybe the center would be 4.5 volts. But if we spin the wiper all the way to the right, most of the resistive material is going to come before the center pin. So it's going to be high resistance, it's going to drop a higher voltage. So the voltage that we might see at the center pin might be like 1 volt or a half a volt. So in the same way, we could wire this up and the center pin could be connected to the Arduino, and as we spin the dial, the Arduino can measure that change in voltage. With push buttons, we want to connect push buttons and switches to the Arduino, but once again, Arduino measures a change in voltage, so we normally use pull-up or pull-down resistors. Pull-up resistors are fairly common. So in this instance, we have this resistor here, and this is an open circuit, so there's no current that can flow. So this, there's positive voltage here, and even though there's a resistor here, because there's no current flowing, there's no voltage drop. So the same voltage above the resistor is present below the resistor. So the output here would be positive voltage. When we push this push button, suddenly we have a path to ground, so current can flow, and now this resistor will drop all of the voltage, and the voltage present at the output will be 0. So by putting a pull-up resistor with a switch, when the switch isn't pressed, the output's 5 volts. When you press the switch, the output is 0 volts. The pull-up or pull-down resistor basically works the opposite. When the push button isn't pressed, you recognize 0 volts, and when you press this, now 5 volts can be present here, and then it's dropped completely by the resistor, and so the output will recognize 5 volts. So yeah, this is how we would connect push buttons or switches or other digital inputs that are either on or off. There's also syncing versus sourcing. Yeah, I didn't know if my computer might block too much of it, but it's easier to think about with outputs, but basically the idea is the controller providing a path to ground, or is the controller actually like providing a path to the positive voltage? So when you sync a load, you bring it to ground. So the load is always connected to positive voltage, but it doesn't have a path to ground, so it doesn't turn on. When you flip the contact in, this says PLC, but we'll say this is the Arduino, it brings this to ground, and now the load can turn on. Sourcing would mean that the Arduino itself provides the voltage, so when you turn it on, it provides the 5 volts out, and then the load drops it and it connects to ground. So typically we connect things, we source outputs, so like with the LED is here and then it's connected to ground, and we provide the 5 volts that turns on the light. And then for inputs, it's similar. Basically, it's whether or not the input, there's 5 volts, and then when you press the button, it provides the 5 volts to the Arduino, or the opposite. I believe with an Arduino, it's a syncing input. So basically, like I said, with these pull up or pull down, you provide the voltage, and then when that's pressed or not, the Arduino can recognize that voltage. It's a little more confusing from the input size, but I hope that kind of makes sense from an output if you're providing a path to voltage or if you're providing a path to ground. So this is the circuit we're going to build. Yeah, we won't quite build it yet because I want to talk about a few things. But as you can see, there's lots of different inputs and there's one output. We're also using the fancy RGB LED. And you'll notice that this potentiometer is acting as a voltage divider because the center pin is connected to an analog input, and then we provide voltage and we provide ground. I don't know if I talked about this in depth last time, but if you looked at Arduino, you'll notice that these pins are all digital pins. So they can be digital inputs or they can be digital outputs. But down here, these pins are analog inputs. So with our inputs that are changes in voltage, we want to connect them to the analog input side. And you'll also notice that this, in a similar way, this photoresistor has a path, or has a wire that connects it to an analog input. And with this photoresistor, we'll have to set up a voltage divider so we can actually measure its change in resistance. Then we also have two push buttons. One of these push buttons has a pull up resistor that's connected to 5 volts, and the other one has a pull down resistor. So whether it's a pull up or a pull down is going to change what happens when you press the buttons, as I mentioned before. And then the goal of this circuit is that each of these is going to adjust one of the channels of the RGB LED and how bright it is. So as you spin this potentiometer, I think the red channel is going to get brighter or less bright. As you change the amount of light that this sees, it's going to change the green channel. And if you push a push button, it's going to increase or decrease the blue LED. So this is what we're going to start building. But before we build it, we're going to have to determine the value of all of these resistors. So I have values right here, but we're going to have to figure out why we picked those values, and the values are going to change for the actual physical demonstration. So this is the formula for determining like the resistor that you would use to reduce the current through an LED. So it's basically V equals IR, but then you divide by current, so you have resistance by itself. So you have resistance over here, you have, desired LED current. Current is the denominator, and then voltage is the numerator. And you want to figure out basically the voltage that's going to be dropped across that resistor. So an LED typically drops some voltage, and then you'll want the resistor will drop the rest. And that voltage drop by the LED depends on what color. So let's take a white LED for example that has a 3.5 voltage drop. So we have 5 volts, a 3.5 voltage drop by the white LED. That means the remaining 1.5 volts will be dropped by the resistor. So now we know the voltage drop and we want a specific current. So with the voltage drop and the current, we can determine the best resistor to put in that place. Also, normally the desired current is between 10 to 15 milliamps. So, did anyone bring like paper and pencil?
I have paper. I don't know if I have a pencil.
Do I have any pencils?
I didn't realize we had to come prepared to class.
Come on, guys. You all are gonna fail.
The actual university class.
I just grabbed it.
Well, there's just a couple quick calculations. You could probably just...
Take like 4 or 5 sheets. There you go. Do you have a pencil?
You got a pencil? Jordan, you have a pencil? You want a pen?
No, I'd have to go run over to my lab.
This is like super basic math.
Sal's holding a pencil.
Yeah. You can use it together, right?
Here, Laura, you have one? Jane, do you have one? Okay.
You want paper?
Yes, please. Thank you.
Like I said, this is kind of embarrassing. It's pretty basic math, but it helps if you have a piece of paper, and it's going to get slightly more complicated. Maybe. So, with our RGB LED, just for fun, let's pretend that we basically have a red, a green, and a blue LED. So using these values and using a desired current of 15 milliamps, we want to figure out what the resistor is for each of those LEDs. For green, you did the highest. Okay.
'cause
I would pick a value in the. I think this is pretty high. I would pick a value in the middle.
So that's 200, 103, and then 200 again.
Okay.
Shouldn't like these be like the same? Because like the middle should be like about the same for both of them. It just wasn't satisfying.
I think this chart might not be the best. I'm pretty sure green should be here and blue should be here. I would use like 3.5 for blue. I would use like 2.5 for green. What?
I would probably just set, like,
Literally,
the
orange is really disgusting.
Probably should have done that. I just found this chart online really quick.
Nobody has been pointing this out.
Oh, I noticed it immediately.
Didn't notice it, but now
Neither did I. Now I can't.
I noticed it the second it switched, and I didn't say anything. So
I did steal this. I did not write orange.
it's like
I don't know in what country they spell it like that.
also like I don't know what language that is. That the water blue is.
That's a good question.
That is, yeah.
That's some Middle Eastern, maybe?
That's what I was
That
thinking.
just says orange, but in like Arabic.
Well, I'm talking about the water part.
This part has no math. It's great.
Let's go.
Nice.
So for
That's what I like to hear.
a pull-up or pull-down resistor, what I found is it's recommended to use a value between 1K and 10K. So for push buttons, normally it doesn't really matter, so just pick 10K, call it good. If you want to know why, basically if you select a resistor that's too low, it's going to draw too much current. So like in this example, if this is really low, then you have 5 volts, a path to ground with very low resistance. Every time you push the push button, you're going to draw a lot of current, and that's just wasted power. So you would think you'd want to make it as high as possible. I'm not completely sure, but there are reasons why you don't want to make it too high. What I read is sometimes like the input pin will leak current. So if you have a really high resistance, then you're going to only have a little bit of current. And if the input pin leaks some current, then you might not even register that the button's been pressed. Also, the higher the resistance, the slower the circuit's going to react because of the RC time constant, resistive capacitance time constant. I don't know, is there something you want to say?
Sorry, there's something I want to say. So this is especially important depending on where you're sourcing this from, or syncing this from. Because for example, if you're sourcing or syncing this from like an Arduino pin, if you choose too low of a resistance, you'll actually destroy the controller. Well, depending on the quality, like how they make the chip, but you could actually destroy or damage the controller because they're only meant to source or sync like 20 milliamps or some small one. So it's especially important.
Yeah. So I would say just use a value of 10 kilo ohms. You'll be good. That's what we're going to use for these resistors. And then the last thing we have to determine is for this photoresistor. As you remember, this is part of a voltage dividing circuit. This is one resistor, this is the second resistor. We have to determine what that second resistor value is going to be. And so these are the steps that we're going to use. That's why I got out the multimeters. We'll measure the resistance of the photoresistor when it's exposed to light and when it's dark. And then we're going to use this equation. The photoresistors are R1, so we could solve this for R2 and then plug in our R1 value and determine what our R2 value is for the given resistance, the given voltage input, and the desired voltage output. So ideally, to get like the full range when we use the voltage divider, ideally when the photoresistor is dark, the output's about 0 to 1 volts, and when the photoresistor is exposed to light, the output's about 4 to 5 volts, and this just gives us the most range to work with, a little bit more precision. So if you guys want to take a photoresistor, does anyone not know how to use a multimeter? Okay, I'll help you. Everyone else do? Okay. So use a multimeter, write down what the resistance is when it's exposed to light, write down what the resistance is when it's completely covered. I would solve this equation for R2, and then you can plug in your desired values for when it's dark and when it's light.
Where's the
We're gonna hear that in the recording.
I'm leaving that in. We're getting demonetized. I kind of want to see if it actually.
This is your fault, Jaden.
We're gonna get the
No more passive income.
There's no yellow dollars.
We're gonna lose monetization.
Yeah.
Of course, it's all about the money.
It's gonna retract response over inflammatory comments. Oh, it's your specialty.
So anyway, so hopefully the code's working for most everybody. If it's not,
Says the software guy.
you can
All
also
my connections are really jacked. Don't worry about it.
you can also steal the circuit on Tinkercad and do it on your computer. And the Tinkercad circuit is perfect, so everything works, including the the photoresistor. The photoresistor is being a little flaky, but we're gonna walk through the code. I don't know if any of you guys took a look at the code while we were doing it,
You mean you didn't just copy paste?
but the code's laid out in like 3 main sections, I guess, 3 big sections, which is just the variables above the code, the setup loop, and then the main loop that runs forever. So in this example, we have 4 different inputs. We have the potentiometer, the photoresistor, the pull-up, and the pull-down. And this is the pull-up button and the pull-down button. And because these pins won't change, their value is going to be the same the whole time, I use this constant before the int. So that's just a way that the code knows that later if I try to set like potentiometer equal to something else, that's wrong, and it can like throw an error, because this is going to remain the same through the whole program. You'll also notice that with the analog inputs, we use A0 and A1, and that just Arduino code is able to know that an A0 is analog 0. And then we also have these LED pins, and we'll talk about in a minute, the LEDs are PWM pins, so they must have a little squiggle. I don't know if I spelled that right. Squiggle by the pin numbers for the red, blue, and green. In the setup, we set the LEDs to outputs, we set the pull-up and the pull-down to inputs, but we don't have to set the analog inputs to inputs because we only have analog inputs, we don't have analog outputs on the A0 through A5 pins. So if you plug anything into an A pin, we know that it's an input. So we don't have to set that up in the setup code.
What would be an analog out?
Well, that would be PWM, which these lights are, which is how we varied the brightness.
Wait, is PWM be analog?
PWM isn't analog, but it's like close.
Okay, I was gonna
It's
say
like
because-
an analog output, but not exactly.
Okay, that's always confusing.
And in the code, you'll see that's how you actually write it. So then in the loop, we have variables to store the values that we read from all our inputs. So we have this potentiometer input value, photoresistor input value. We have I called them flags. They're bools because they're either going to be 0 or 1 for the buttons, for increase and decrease. So one of the buttons increases it, one of the buttons decreases the brightness. And then we also have the red out, blue out, and green out. And then we read in the inputs from all of our inputs. So for the analog pins, we do analog read, and then we put in the pin variable, and it's equal to the value. And then for the push buttons, we do the digital read. Does that all make sense, everybody? Now, the problem, we don't really have a time to get into it too much, but when you're doing an analog read, I think it's a 16-bit number, which means it varies between 0 and 1023. But when you do the PWM output, which you'll see in a second, then that changes the brightness of the LED. That value can range between 0 and 255. So we have one value that's between 0 and 1023, and we basically want to constrain that in between 0 and 255. And so we could write our own code that does that, but Arduino has a helpful map function. So you pass in a value, you pass in currently what's its lowest and what's its highest values, and then what do you want to map it to. Yeah, it scales the value that you give it in between the range that you give it to a new range. So this is very helpful because a lot of times you will do this example where you read in an analog input and you want to send a basically analog output, a pulse width modulated output, and you need to scale the value. And so you just pass in to the map function the value that you read, 0, 1023, 0, 255.
Oh, is this scaling the duty cycle? From like 1-bit resolution to another?
Yeah, this is basically 16-bit resolution and this is 8-bit resolution.
That's not 16-bit. That's like 9-bit, I think. Or 10-bit.
What's 8?
16-bit
What's
is like
two?
65,000. It's quite large.
Maybe I'm wrong. So what's...
That's 10-bit.
That doesn't seem...
Is that the
I do...
analog to digital converter resolution?
2 to the 10th. Why? Okay. I don't know why it's 10. That doesn't seem as like a standard. I don't know why. I just assumed it was 16, but yeah, you're right. I don't know why it would be 2 to the 10th. This is 2 to the 8th. So yeah, I don't know. That's just the standard analog input resolution, I guess. And I guess that makes sense that they can only make it go so high. They're not going to make it 8 or 16. They're going to make it whatever they can make it.
And then the PWM only has a resolution of 8-bit.
Yeah.
Okay.
Yeah. Between 0 and 255. At least in the way the Arduino does it. So then remember if statements. We have 2 different if statements that read in what flag we pressed. And you'll notice this triggers, so this green out value plus plus, we're increasing the green value. Green out value minus minus, we're decreasing the green value. But this triggers when the increase flag is false, and this triggers when the decrease flag is true. And that may seem weird, but if you remember back to one of them's a pull up and one of them's a pull down. A pull up resistor and a pull down resistor. So the increase flag is the pull up resistor, so it's actually normally going to be true, and when you press the push button, the output's false. And decrease flag, which is the pull down resistor, normally it's false, and when you push the button, it's true. So you just have to remember that when you wire up your circuit, you have to think about whether you're using a pull up or a pull down resistor, and then what the voltage is going into the Arduino at what point. So I just threw both of them in to show the example of both. Finally, down here, we change the brightness of the LEDs, and we use this analog write, which you may notice that we're using digital pins, but we can use analog write on the pins that have the little squiggly line because they're PWM enabled. And so we can pass in the LED, the value of the LED that we want to change, and then the value we want to change it to. So this red out value and blue out value is what we map to here. Red out and blue out value. And then the red, blue, and green are just the value of the pin. So does that kind of make sense for some of these syntaxes that we haven't seen before, like the analog write, the map, we talked about this before, but the static int and the constant int. Does anyone have any questions about that?
For the map, what do we... is that for the pot value that we're reading? in converting to PWM?
Yeah, that's for the potentiometer and the photoresistor.
Okay.
So both of those are analog inputs, so they're going to be mapped, like the value that we get is going to be in between 0 and 1024. And we need to map that to 0 to 1024. We need to map it between 0 and 255.
I guess to clarify that further, just I kind of already asked this, but if that was like 80% of that, like 8,000 or whatever, it would be 80% of 255.
Yes, yeah.
I guess, how do we know that it's 1023?
If we read the documentation, that would tell us that that's the max value. Also, if you just like pulled it up, if you pulled it up on the serial monitor and checked the max value and the min value, it'd be very close to this. That's just the analog input. The way it works, it has to have some limit of the highest value it can read in, and they, not arbitrarily, it's based on hardware, but they basically arbitrarily decide that that's going to be the maximum value that they can read in.
The reason it's that very specific value is that's 2 to the power of 10. So
I was just
yeah.
asking where you find it
Yeah.
from, like
Okay.
how you.
Yeah, I mean,
You know it now, so you never have to find it again.
if you look at the documentation,
You know
it will-
because
it'll
Joe
say something
told
like
us.
10-bit
Exactly.
resolution.
Okay.
So in that case, you would find that value by like, if it says it's like an 8-bit resolution, that max number would just be 2 to the power of 8. That's 255.
Yeah, I knew this was 8-bit, and then I guess I just assumed that was the next highest. But as I was saying that, I was like, that is pretty low.
Yeah.
Okay. So then the last thing, this further reading section,
Whoa.
is what I was talking about, is the PWM channels. So on our Arduino, we have 6 different PWM channels. It's the digital I/O with the squiggly line. And so on these pins, you're allowed to do the analog write. And I've talked about this before with the electric team, but analog write is PWM, which is pulse width modulation, and it's where the Arduino turns a pin on and off like rapidly. It'll turn it on for a period of time and then turn it off for a period of time. And there's different, based on that timing, you can get a different percent that you're on or off. So in this example, you're on 0% of the time. This example, 25% of the time. Example, 50% of the time. And it turns on and off so fast that in this example, for the LED, it's blinking on and off so quickly that you can't even recognize it. Another example when this could be used is for spinning motors, because with motors, you don't want to like send it less than the voltage that it's rated at. You want to always give it the voltage that it's rated at. But if you want it to spin slower than its normal RPM, you can just pulse it. And so if normally it spins at 100 RPMs and you want to spin at 50 RPMs, you pulse it 50% of the time. I don't know if that math would be perfect, but it should reduce it and it'll spin slower. So pulse width modulation you're allowed to do on some of the pins on the Arduino, and then you're allowed to do the analog write function in the code. So yeah, that's the conclusion. Any final questions on PWM? Or any syntaxes, any wiring? I know the wiring took a long time today. Hopefully it's not always like this.
It will be.
I had fun.
Alright, well, thanks everyone for showing up.